Now that we know a little bit about the importance of compounds in the basic structure of an atom, we're going to talk about chemical bonds, since that's what we need for compounds to form. Remember that elements are the pure fundamental type of different substances, meaning that they cannot be broken down into other substances by ordinary means. Compounds, on the other hand, can be. When we talk about elements, they're often organized in a periodic table. Atoms with similar properties are going to be organized together. For example, lithium, sodium, potassium, rubidium, cesium, and francium are all explosive. The number in the box indicates the number of protons that the identity of that atom requires. So sodium has 11 protons, whereas potassium has 19. The specific combinations of electrons, negatively charged particles, protons, positively charged particles, and neutrons, neutrally charged particles, are what determine the behavior of an atom. The arrangement of electrons around an atom determine how active that atom is. Electrons are arranged in shells around the nucleus of the atom. These shells accept, give up, or share electrons until they are filled. Notice that the inner shell only contains 2 electrons for this fluorine atom, but the outer shell contains 7. Most common elements have filled outer shells with 8 electrons. This means that fluorine's shell is not filled. Atoms bond to each other by filling the outmost or valence shells. So the number of electrons required to fill the shell is related to the number of bonds that an atom can form. If we look closer at the atoms in the periodic table, you'll notice that the outer valence shell has the same number of electrons as we travel down. Hydrogen has 1, lithium has 1, sodium has 1. These electrons are extremely happy to give away that extra electron. Remember that electrons are energy, so giving up that energy makes them highly reactive. In fact, they're explosive. The opposite of these atoms are what we call the noble gases, things like helium, neon, and argon. Notice that all of the outer valence shells for these atoms are full. That means that these atoms are already stable and don't have very much interest at all in interacting with other atoms. It's important to note that all of the atoms, as displayed on the periodic table, have a neutral charge. But not all atoms, as we encounter them, are in that position. Atoms are molecules that have an electrical charge due to a transfer of an electron, i.e., a gain or loss, are called ions. The neutral atom of sodium has 11 electrons. This balances out the 11 protons that sodium has. However, this means that there is an electron that is alone in the outer valence shell. This is highly unstable. When the sodium atom gives up this extra electron, it becomes an ion of sodium and has a positive charge. This is because it now has an excess of protons, 11 of them, to go with its 10 electrons. This results in the outermost shell of the atom being full, creating a more stable atom. Atoms want to be stable, so they're going to move in whatever direction is required to make that possible. We can also have a situation where electrons are gained. For example, the neutral atom of chlorine has 17 electrons to balance its 17 protons. Notice that its valence shell has 7 electrons. Accepting an electron from a donor, like sodium, would allow the valence shell to be full. When that happens, chlorine becomes an ion of chlorine and has a negative charge because it has one more electron than it had before. As you might imagine, these types of ions have special names. Cations are positively charged, like the sodium ion we discussed, where anions are negatively charged. If you have trouble remembering these terms, you can try to remember them like this. Cations are like cats because they're positive, whereas anions are like onions. They're negative because they make you cry. Cations are usually formed by metal atoms, and anions are usually formed by nonmetal atoms. Cations tend to be attracted to cathodes, which also have a negative charge, whereas anions are attracted to anodes, which have a positive charge. This will be important later when we talk about things like electrophoresis at the end of the semester. It's also important for working a battery. This is why lithium ions are so useful for battery formation. And last but not least, cations and anions tend to form electrostatic interactions with each other. This means that they're attracted to each other due to their electrical charge. So how do two atoms combine? Usually this occurs through chemical bonds. These cause a union between two atoms and occur by transfer or sharing of electrons. For example, this water molecule is a compound that is formed by chemical bonds. A compound is two or more elements bonded together, and the ratio of each element is in a fixed proportion. A reaction happens anytime atoms or compounds are rearranged to make a new compound by breaking or making chemical bonds. Reactions are often written like this. On the left, we have what we're starting with, the reactants, and on the right, we have what we're going to get, the products. In this case, the reactants are 12 water molecules and 6 carbon dioxide molecules. These are rearranged to produce 6 oxygen gas molecules, 1 glucose or sugar molecule, and 6 water molecules. If you were to add up all of the hydrogens, carbons, and oxygens that exist in the reactants on the left, you would have the same number in the products on the right. This is important because matter cannot be created or destroyed. Anytime you see a reaction, it's always going to be written this way, with the reactants on the left and the products on the right. Notice that the arrows denote the direction in which these things change. When you see double arrows, that means that the reaction is reversible. This rarely occurs in nature, but it can occur spontaneously in a laboratory setting. So how do you know if a chemical reaction has happened? Generally, you want to look for things like emergent properties. These might be something like a change in color that is not consistent with the original chemicals, formation of a precipitate or suspended solid where there wasn't one before, the formation of a gas when one wasn't present before, a change in odor, or a change in temperature. The types of bonds that occur during a chemical reaction fall into three major categories: ionic bonds, covalent bonds, and hydrogen bonds. Ionic bonds form when one atom loses electrons and another atom gains electrons, such that the opposite charges of the ions hold them together. For example, when a sodium ion gives up its electron to a chlorine atom, the sodium ion becomes positively charged while the chloride ion becomes negatively charged. These two charges, which are opposite from each other, then attract. Ionic compounds are generally referred to as salts and form between a metal and nonmetal atom. Some of them form crystal structures like the table salt that you're used to seeing every day. Covalent bonds work a little differently and usually occur when more than one electron needs to change space. For example, oxygen atoms have 6 electrons in their outer shell. In order to be happy, an oxygen atom would need to give up 6 electrons or gain 2. However, oxygen atoms are usually found together. Because both atoms only need 2 more electrons, they can share these electrons. Since neither atom is able to give up the electrons, they stay close together, with these electrons spending some of their time in the orbit of one molecule and some of their time in the orbit of another. There are two types of covalent bonds. Polar covalent bonds, like the one between oxygen atoms, are equal sharing. This usually involves atoms of the same element, but sometimes occurs between carbon and hydrogen. Polar covalent bonds involve unequal sharing. This occurs in things like water, carbon dioxide, and ammonia. This occurs because one of the atoms has a slightly higher pull than the others. This means that the electrons spend most of their time around this hogging atom. Because of this, polar covalent bonds often result in molecules having charges. In the case of water, the oxygen pulls the electrons from the two hydrogens closer to its core. This results in the oxygen being slightly negatively charged and the hydrogens being slightly positively charged. Since positive and negative charges can attract one another, compounds with polar covalent bonds can sometimes be attracted to other compounds with charges as well. One of these is a special type of attraction that we call hydrogen bonding. While hydrogen bonds do form between other compounds, we will primarily focus on their function in water. This brings us to the topic of water's life-supporting properties. Hydrogen bonds are weak bonds, but they are important in the chemistry of life. This is because hydrogen atoms of water molecules are attached to oxygens by polar covalent bonds. The slightly charged hydrogen atoms form these weak bonds with negatively charged oxygen molecules in the neighboring water molecule, and that these weak bonds constantly break and reform. Hydrogen bonds make water molecules stick to each other. This results in water being cohesive. If you were to drop a coin or skip a stone or drop something else into water, you would notice that the water is pulled downward and then bumps back up. That is because individual water molecules are slightly attached to all the other neighboring molecules. This also allows water to have a high degree of surface tension, which is why insects like this boatman can walk across its surface. We can also see the strength of this kind of surface tension by thinking about how many drops of water we can fit on a coin. Notice how the water is pulled up and doesn't just flow over the side of the coin as each drop is added. Although it appears that the water may at any time flow over the side of the penny, we can add substantially more drops before that will happen. Eventually, the weight of the water itself at 36 drops overcomes the surface tension and allows the water to flow off the side of the penny. Cohesion is also important for allowing plants to breathe. This is a process called transpiration and will be important in 102. In addition to allowing water molecules to stick to one another and to allow plants to transport water, hydrogen bonds also help regulate heat. Heat is absorbed when hydrogen bonds break and released when hydrogen bonds form. This helps water regulate temperatures and keep them relatively steady. As the most energetic water molecules evaporate, breaking all of their hydrogen bonds, the surface of the substance can cool. When a substance evaporates, the surface of the liquid that remains behind cools down. This is called evaporative cooling. So, how can hydrogen bonds do this? Well, temperature is essentially how fast molecules are moving. Extensive hydrogen bonding in liquid water restricts molecular movement by binding all of the water molecules together. The molecules of any substance are always moving or vibrating, but this restriction prevents the temperature from rising higher until the hydrogen bonds are broken. This means that water can absorb a lot of heat before changing temperature, because to raise the water's temperature, we must first disrupt those hydrogen bonds. This is why it takes so long to boil a pot of water, and it's also why places that are located near oceans tend to have more stable temperatures than those located inland, far away from large bodies of water. Water also serves as something called the universal solvent. This means that it dissolves more types of solutes than any other solvent known to man. This is because it's polar and can dissolve any substance that has any degree of polarity. So it's the solvent found in all cells, as well as blood, plant, and tissues. The way that this works is that the water molecules use their charge to separate ionically bonded materials, such as this sodium chloride. Polar or charged solutes that are dissolved in water form what we call an aqueous solution. If the water were removed, these would go back to being sodium chloride. Aqueous solutions often have what we call a pH. pH is essentially the measurement of ions that are present suspended in the water. As the number of hydrogen ions increases, we would say that something becomes acidic. However, as the number of hydroxide ions increased, we would consider that to be basic. Acids contribute hydrogen ions to solutions. You'll notice that each of these listed acids have a significant number of hydrogens that are available to separate from the molecule when added to water. Bases, on the other hand, reduce the number of hydrogen ions in solutions. This means that they often take up those ions. They might also give off hydroxide ions to the solution. Buffers are substances that keep pH relatively constant. An example would be your blood plasma. The way that they work is by accepting hydrogen ions when there are too many of them and donating hydrogen ions when there are not enough. This is really important for keeping your blood neutral. As we discussed at the very beginning of Chapter 2, carbon dioxide, when dissolved in water, increases the acidity of the liquid. Since your blood needs to transport carbon dioxide, it needs to have a way to do that without increasing the acidity of your blood. The buffers present in your plasma are how they do this. You'll learn more details about exactly how this works in 102. Another important feature of water is that it can exist as a gas, liquid, or solid. While there are other compounds that are able to do this, water is less dense as a solid than a liquid because of hydrogen bonding. This is a unique property of water and is what allows ice to float. The reason that this happens is as water molecules slow down, remember temperature is based on the speed or movement of those molecules, hydrogen bonds actually push the water molecules away from each other. This is why water expands when it is frozen, and also why it is less dense and able to float.